Welcome all to this another presentation as part of the Thermal Transport Cafe. Today we have Dr. Allison Mahvi, who's a Bluemke Assistant Professor in the Department of Mechanical Engineering at the University of Wisconsin-Madison, where she leads a lab called the Lab for Energy Transport and Storage. She received her Ph.D. in Mechanical Engineering from Georgia Tech in 2018 and her BS from the University of Wisconsin-Madison in 2012. She did her postdoc at University of Illinois Urbana-Champaign from 2018 to 2019, and then in the National Renewable Energy Lab from 2019 to 2022. The research focuses on two-phase flow, surface enhancements, advanced thermal energy systems, and thermal energy storage devices, which have resulted in 25 peer-reviewed journal publications. During her graduate work, she received several awards, including the ASME Graduate Teaching Fellowship, the Nunn Security Program Fellowship, the Woodruff Fellowship, and the ASHRAE Grant-in-Aid Award. And today she'll be talking about her work on tryout of thin liquid films in annular flow.
All right, great.
Dr. Mahvi.
Thank you. Yeah, thank you very much. So as Vikram mentioned, I'm going to be talking about thin liquid films and annular flow and some of our modeling and experimental work in that space. My areas of research are in thermal energy storage, heat and mass transfer, and two-phase flow. Today, I'm going to specifically be talking more about two-phase flow. But before I get started, I'd like to acknowledge the people that are working, that did a lot of this work. Argenthal Bernson, Joe Farrell, Tyler Lee, and Sage Slater, who are doing different aspects of annular flow experimentally and developing models that predict dry out in these different flows. I'll also acknowledge some of my other collaborators as I go along. As Vikram mentioned, I run the Laboratory for Energy Transport and Storage. We do a lot of work across different scales, from fundamental transport to system analysis and demonstration. In the fundamental transport space, we do a lot of coupling of modeling and experimental work, looking at things like annular two-phase flow, flow boiling, direct contact condensation, and other things like that. This video on the bottom is an example of a direct contact condensation experiment we're looking at. And we try to develop models that can predict things like acoustics, in this case of condensation, or dryout CHF, or heat transfer coefficients in the case of flow boiling, and use our experiments to validate models and try to understand the physics of the flow better. We translate that work into developing components for different energy systems. This is an example of a thermal energy storage heat exchanger, so a little different from the modeling and two-phase flow work that shown on the left. Here, we're looking at how do you design a thermal energy storage heat exchanger using different types of modeling approaches. And then we test those components in a hardware in the loop setup. We have a couple of these in our lab to make sure that the models that we're generating predict the flow well. And then we generally translate these components into systems. We've done some system demonstration type projects, some analysis around trying to understand if you optimize energy systems, you can quantify things like the operational costs, how do you optimize how you control the system, things like that. So generally, we try to get all of these different pieces to feed into each other and get a much better physical understanding of how two-phase flow and energy storage works inside of larger HVAC and power generation systems. So today I'm going to talk mostly about fundamental heat transfer, looking at flow boiling. Before I get started, I want to define critical heat flux. I think a lot of people work in this space, but just to get everybody in the same footing, critical heat flux, or CHF, is when a heated wall is exposed to a vapor. Vapors are generally poor heat transfer fluids, and so you get a sudden and significant drop in the heat transfer coefficient. This can have different results depending on what type of system you have. So if you have a heat flux boundary condition, that's something like a nuclear reactor, cooling of chips, where you have just a heat flux that is going to keep, or some object that's going to keep generating heat. If you drop the heat transfer coefficient, you need a larger driving temperature difference to dissipate that heat. And so the heated surface tends to become very hot. In different scenarios, it can damage or destroy the equipment. And generally, that means that boiling has a very high heat transfer coefficient, but it's usually used conservatively in cases with a constant heat flux boundary condition because you don't want to destroy your equipment. You need a really strong understanding of when critical heat flux will occur so you can operate far away from that case. In temperature limited cases, this is an example of a vapor compression system. The outdoor coil in this case is an evaporator, so it does have flow boiling inside of it. Industrial heat exchangers, there's lots of other power generation systems have heat exchangers in them that have two-phase flow. If you have critical heat flux inside of these components, generally you're just decreasing efficiency. You have to increase the size of the heat exchanger components. There's a lot of disadvantages to going to critical heat flux, but you're generally not going to destroy the equipment. So it's just kind of different scenarios of what can happen when you reach a critical heat flux case. There's two different types of critical heat flux that I'm going to talk about. We're going to focus on dryout critical heat flux, which is when you have an annular flow. On the left, you have a boiling case where the fluid's coming in subcooled. It's boiling through this channel. You get a film that forms on the surface and eventually dries out. Generally, it starts by this thin liquid film breaks up because it becomes too thin. It's not stable anymore. You start getting this transient dry out where you get these little dry patches that form between disturbance waves, and then eventually the whole surface dries out. And you get this drop in heat transfer coefficient that's associated with that. Generally, the goal of dry out CHF is, in some cases, you don't need to fully evaporate the flow, so you just want to stay away from that. You want to stay at lower qualities and avoid it. But in a lot of cases, you want to delay CHF. So you want to delay it to as high a quality as possible so that you can shrink down the size of your heat exchanger. You don't have this region with a low heat transfer coefficient. The other case of critical heat flux where you get a vapor that's in contact with the wall is called departure from nuclear boiling, or D&B. This is where you get lots of these vapor bubbles. They crowd the surface. They start conglomerating on the surface, and you get a vapor blanket that causes film boiling. So all of the heat then needs to transfer through the vapor before it can start evaporating the liquid. You just generally want to avoid this at all costs. There's been a lot of research around departure from nuclear boiling. A lot of it's been focused on the nuclear industry, and there's been work in trying to increase the heat flux that D&B occurs at, but generally we want to know it with very high certainty. Where is this limit? When are we going to get to D&B? I'm specifically going to talk about dryout CHF. There's been less work around that. And we have been doing some interesting modeling around that space to try to understand when it will occur, with the goal in the future of looking at how can we change the surface or what can we add to the surface that will impact dryout CHF. So if you look at CHF modeling approaches, there's a range of complexity. On the simplest side, there are a lot of empirical curve fits or lookup tables that look at taking a lot of experimental data, some database with many, many different boundary conditions, ideally lots of different types of fluids. Some of them are around a single fluid, some of them have lots of different fluids in them. And usually you try to non-dimensionalize different parameters that are important and then fit the data so that you can predict things like CHF or heat transfer coefficient. There's a lot of advantages of these types of correlations or lookup tables, and they're commonly used. mainly because they're really easy to implement. You can write an equation, it's one line of code, something like that. The challenge is that it's not very easy to transfer. So if you want to translate to some other fluid or some other flow condition that's not in your database, you don't have very high confidence that you're going to get the right CHF or heat transfer coefficient value. In a sort of intermediate complexity, there's mechanistic models. These usually try to discretize the flow in the flow direction and get an idea of how the different main properties of the flow interact with each other. This is showing an annular flow case that's looking at the liquid film and a vapor core. There's other kind of other versions of this type of thing. The advantage of this is that it reduces computational time a lot from more complex models. You could theoretically translate to other fluids because you're doing a better job at trying to identify the physics that's happening. But the problem is they usually rely on closure relations, which we'll talk about. And so you need pretty good closure relations in order to be able to translate between fluids. And then on the most complex side is computational fluid dynamics models. These are where you discretize the conservation equations in 2 or 3D. They can be very computationally expensive, which is why they are not used generally for very large kind of time-dependent data sets, but they can be very useful at translating to different fluids or different scenarios that are not a standard constant heat flux or something like that. We're specifically going to talk about the mechanistic model area, trying to understand what are the main features of the flow, what impacts dry out, and try to look at how well that might translate. So to look at mechanistic models, we first need to understand what are the main features of the flow and what is driving something like critical heat flux. So in our work, we're specifically looking at annular flow, where you have a thin liquid film that covers the surface, and then you have evaporative film boiling through kind of evaporating the fluid at the liquid vapor interface. You tend to have very high heat transfer coefficients in the annular flow regime until you get to this intermittent dryout case where you get some regions where the heated channel has a vapor in contact with it. So I'm going to show a video in a second. There's fluid that's flowing from the bottom of the video to the top. There's this annular film on the surface of a glass channel, and then there's a vapor core going through the middle of it. So there's a couple main features that I want to point out. The base film, which has these small sort of ripple waves on the surface of it. Oops. It tends to be very thin and relatively calm. There's these droplets that are kind of these blurred lines. You can't see them very well that are going through the center of the channel. And finally, this darker region is a disturbance wave. That's a thicker region of the flow. It's a wave that's moving over the surface of the base film. They tend to be very turbulent kind of structures within the flow and end up having a pretty big impact on dryout. So this is just a schematic of the same thing. So here's this disturbance wave. You have these disturbance waves on top of a base film. The base film tends to have these very small waves in it that they don't have a huge impact on the total heat transfer coefficient or CHF. And then there's these droplets in the flow. They tend to be moving with the vapor core, moving pretty quickly, and they come from these disturbance waves. So they get these little droplets that get ripped off of these waves, and they stay in the vapor core. They tend to be hard to evaporate because they're not very close to the heated channel. So these are the main features: droplets, there's vapor core, a disturbance wave, and a base film. The disturbance waves are pretty important. They carry a lot of the liquid mass. They're pretty thick, they're turbulent, they're carrying a lot of mass in the flow. And when the flow is intermittently drying out, you get these dry patches that form. You can see it in this video. And then these thick waves come and re-wet that surface. And so right as you're starting to dry out, the waves are what's keeping the surface cool. And then when they can no longer do that, maybe they're spaced too far apart, or they're not carrying quite enough mass to fully re-wet the flow, then you get to this more severe dry out case where the whole surface dries out. Dry out has the disadvantage of dropping the heat transfer coefficient, but in some cases, if you have impurities in the flow, for example, they tend to deposit on the surface, on the heated surface in this region that's drying out. And so that can be another sort of issue in your flow. You need to deal with corrosion and deposition of different impurities in this region. So kind of sticking with the same, kind of looking at different fidelities of models. For the mechanistic models, specifically of annular flow, there's, again, different complexities of them. On the far left side here, this is looking at a mixture model. This looks at the vapor core and the liquid film separately, has conservation equations for each of those separately. And there's been a lot of literature on mixture models. It's in lots of textbooks. People use it a lot to try to understand what's happening with liquid films and that kind of thing. In the 70s, this mixture model, a couple different research groups looked at trying to add more features of an annular flow to it. So instead of just having a liquid film and a vapor core, it also measured all of these little droplets and tried to add that feature into the models, looking at entrainment of droplets, deposition of droplets onto the liquid film, trying to get closer to reality, getting a better prediction of heat transfer coefficient, a better prediction of CHF. And then in 2022, one of our collaborators, Jean-Marie Lecour, developed a 4-field modeling framework that looks at the base film and the waves separately to try to get more at intermittent dry out, try and predict dry out a bit better. Some of the motivation for this was actually also looking at impurity deposition, when that might occur when you get really, really thin base films. And so we've been developing that code with him, trying to come up with a model and supplying experimental data to that model to improve the fidelity of it. So just give a little example of the 4-field model. I'm not going to go into lots of equations. I'm not going to talk about it in detail, but this is an example of the conservation of mass equations for the base film and the waves. And one thing to note is that there's all of these terms that are looking at how does the film interact, or how do these different fields interact. So in the base film, for example, there's deposition of these droplets into the base film, vaporization of the base film due to the heat flux that's applied at the surface, and then mass transfer between the waves and the base film. To get at some of these properties, we need to know things like the wave shape and the surface area, the equilibrium base film thickness, the time scale to return to equilibrium state inside of an annular flow, and wave frequency and wave dynamics. So there's a lot of these other pieces of information that we need to know. They're generally hard to measure. And so we wanted to get a better idea of how those pieces worked. Jean-Marie Lecour, the person that originally developed this model, this year at NREF did more of a validation study looking at prior work. First from Wirtz, who was looking at adiabatic annular flow of water at 7 megapascals. And Jean-Marie looked at, or compared his experimental data to the 4-field model that he developed originally, and then found that it compared well for things like base film thickness, wave velocities, wave number density, things like that. So good agreement between the adiabatic data and this modeling approach. He also looked at the non-equilibrium, how it returns to non-equilibrium. So this is a data set where the left side of the x-axis is a heated section, and the positive side to the right of this dashed line is adiabatic. we're trying to come up with how the film reacts to this change in boundary conditions. And generally, we found the model is these lines and the experiments are the points. We found generally the right trend in the data, although this needs more work in understanding how this non-equilibrium transition happens, getting more data for more cases, and yeah, kind of diving into it in a little bit more detail. But we did have generally the right trends. With one of my collaborators, Juliana Duarte at University of Wisconsin, who's in the nuclear engineering space, as well as her student, Cole Dunbar. We're trying to first take this model that we developed and move it into a more complex system. So that experimental data from the last slide was a single channel flow going through the single channel, and it had a relatively simple boundary condition. We took the same modeling approach and tried to apply it to a boiling water reactor, specifically looking at these CAFE thermal hydraulic experiments, where they were testing a fuel or a rod bundle of a boiling water reactor at prototypical conditions. So we're working on the second portion of this, but the first portion was looking at, okay, we have a 3-field model. We want to understand when we'll get to the critical bundle power for this rod bundle. We used the code that we developed and looked at the steady state data with an axial power profile. It's like some cosine profile for heat flux along the length of the channel. And on the y-axis is the model predictions, and the x-axis is the experimental critical bundle power. And generally found great agreement at steady state. So the model did really well. This is encouraging. It did a little better than we were expecting, actually. And then we're still looking at this transient data. So if you have one of the things that makes some of these mechanistic models shine more is when you have really complex boundary conditions. Maybe you have something that's causing oscillations in your flow, some instability, and you want to understand how the surface temperature is going to oscillate. It's hard to find something like that in a lookup table. And so you can use these mechanistic models to get there. Just a note, this is a very different case. It's not a single channel. And so we did have to change our code slightly to deal with all of these spacer grids. So boiling water reactors tend to have spacer grids as you move up the channel, and those distribute the droplets. So the droplets in the vapor core get maybe redirected at the surface and can re-wet the surface. And so we kind of made some assumptions about how that happens inside the model, which helped with the fit here. Okay, so what I've talked about so far has only been water. So the vast majority of past work in critical heat flux has been for high pressure water systems, and a lot of it's been motivated by the nuclear industry. But it's not clear how we take models that were developed for water and translate them. And specifically for this 3- and 4-field approach, there's a bunch of closure relations, like things like droplet entrainment, that are baked into the model. And we wanted to understand how important are those models? How do they capture other fluids well? And is it transferable? So if we want to look at a totally different situation with a different fluid, a different system, will we be able to do that? So just to give a little example, this is a refrigerant. These are different refrigerants. Over the last several decades, the refrigerants have been phased out, the refrigerants used in vapor compression systems, to try to lower the global warming potential of them, make them more environmentally friendly. And so this is an example of some of the refrigerants that we've kind of gone through. R22 has been phased out. There's been a lot of work around natural refrigerants in the last several years. But the properties as you switch refrigerants change. So the enthalpy of vaporization, for example, density ratio, Weber number, they can be pretty different between different refrigerants. So typically what you do is you run a new set of experiments, make sure your existing models work or try to tweak your existing models for this new refrigerant. We're trying to kind of skip over that step and just use some sort of mechanistic model, hopefully that captures the physics well, to get to the critical heat flux. If you look at kind of our current model, we've been looking at boiling water reactors. The properties are just very different than a refrigerant. So the enthalpy of vaporization is much, much higher. Density ratios tend to be a little bit lower. And the Weber number is much different than a refrigerant. And so it's not clear that it's transferable. All right. So I'm going to switch a little bit to the experimental side. So we've been running some refrigerant experiments, trying to feed data into these 4-field models to get a better idea of when you might get to CHF for different fluids and make it more transferable, ideally. This is a schematic of the setup that we're using. The goal of the setup is to visualize upward evaporating refrigerant flows in our test section. And we want to condition the refrigerants to be at a set pressure, mass flux, quality coming into our test section, and then evaporated at different rates to see what is the critical heat flux in different scenarios. The way that this facility works is it's relatively simple to set the inlet condition. We have a big storage tank of refrigerant. We're pulling liquid off of the bottom of that tank and subcooling it and sending it through 2 different pumps. On the liquid side, we just measure all of the properties of the liquid and send it into a mixing tea. On the vapor side, we again measure all of the properties, but we send it through an evaporator first. So we fully evaporate the flow so that it's a superheated vapor that goes into this mixing tea. And then we can control the flow rates of the pumps to control the quality and the mass flux going through our test section. We then have a long developing section going up to our test section, and our test section is electrically heated to look at the properties of the flow. We're specifically trying to measure dryout CHF, heat transfer coefficients, pressure drop, dry fraction, amount of time that the surface is liquid and the amount of time the surface is vapor, as well as the film thickness. So this is a picture of our test section. We send refrigerant in through the bottom at some pressure. Most of our experiments are run right around ambient temperature. This is nice because it makes it really easy to change the conditions. It's pretty fast to get it up and running. And then quality is between about 0.4 and 1. Mass flux is between about 100 and 200. If you look at a cross-section of the channel, looking up, you can see that our channel is rectangular. It's 36 millimeters by 12 millimeters. This is all annular flow experiments. And so there's a liquid film along the surface of the channel, and then a vapor core through the middle. There's a glass pane on 2 of the sides, along the 2 long sides of this rectangular channel. It's coated in an FTO coating. We pass a current through it and Joule heat it. And then in some cases, we have a little obstruction on the surface. Some cases we don't. The point of the obstruction is just to understand how liquid films respond around solid surfaces. Talk about it a little bit. The optical window is really nice, having this transparent window that we can heat, but we can still see through. So we can do flow visualization using a high-speed camera, and we can do a lot of optical measurements. So these liquid films tend to be very thin. If you start putting sensors inside of the liquid film, it can be a problem for measuring what you want to measure. And so we really try to use optical techniques and try not to put anything inside of the flow channel. And then beyond all of these optical measurements, which I'll talk about in a minute, we do measure things like the surface temperature, the saturation pressure, pressure drop, heat input, things like that. That gives us things like the heat transfer coefficient, which is a helpful property for us. So I want to talk through some of these optical measurements. We specifically try to use optical measurements that aren't super complicated, that are pretty easy to implement. on the side of our test section, so that we can get a lot of data from these pretty quickly. We can change things very quickly, and it's not very sensitive. So the first thing that we measure is dry fraction. This is the amount of time that the surface is vapor versus the amount of time the surface is liquid. The way we do that is we use a laser, we direct it at the test section at a specified angle, and we measure the amount of light that gets reflected into a photodiode. This light passes through the glass of our test section, this heated glass. And if there's gas on one side, there's a really big index of refraction change between the glass and the refrigerant vapor, and more of the light will get reflected back at the photodiode. Whereas if it's liquid, there's a smaller difference between the index of refraction, you get less light reflection back. And so we really look at the intensity ratio of the light incident on the test section versus the amount coming back. And this is an example of the type of data we get: intensity ratio on the y-axis and time on the x-axis. When the intensity ratio is small, the surface is coated with liquid, and then when you get this spike in intensity ratio, you have vapor on the surface. And so we're really looking at kind of the time comparison between these two things. It can tell us frequency of waves, it can tell us other things, it can help us predict heat transfer coefficient. And you can collect a lot of data because you're just measuring a single point using a photodiode. You can measure it at a really high frequency and you can get a lot of data points, which is helpful. This is an example of what we use that data for. This is a time series of an experiment. On the x-axis is time, on the y-axis is the effective heat flux, which is this black curve. We're stair-stepping the effective heat flux. We're increasing the power going through this coating on the glass channel until we get to dryout. And then on this kind of orange color is the intensity ratio. You see these spikes near the end, there's a lot of these spikes in intensity ratio. That's telling you dry out, so how often the channel is dry. And then finally, we have temperature on here. The blue line is the saturation temperature of the refrigerant. The red line is the surface temperature of the channel. And you can see in general that the more dry the channel is, you start getting this increase in the surface temperature and you get to this dryout heat flux. The first time the channel becomes dry, these sort of intermittent dryout cases at lower heat flux values, you really don't see an appreciable change in the heat transfer coefficient for those cases. So to look at this a slightly different way, heat transfer coefficient, look versus vapor quality. Here you can see the heat transfer coefficient for those tests, a similar set of tests from the previous case. You get intermittent dryout at some point in these experiments, and you start getting some of the channel becoming dry. So this dashed line is the temporal dry fraction, how much of the time the channel is dry versus wet. You need to get past a certain threshold, like the channel is like a little blip every once in a while, the channel becomes dry. It doesn't really impact your heat transfer coefficient much. Whereas if the channel is dry for a large period of time throughout the test, you get this really sudden drop in the heat transfer coefficient at some quality. So that's dry fraction, one thing that we're measuring. The other thing that we're measuring is trying to understand the disturbance waves. We really want to get at like how the disturbance waves are dynamically changing, how they are impacted by boundary condition and operating condition. And the way we do that is by measuring the liquid film thickness. So again, there's lots of different ways to measure the liquid film thickness. We wanted something that was optical, an optical approach, and something that was pretty easy to implement. So this setup uses a laser. You direct the laser at the glass channel, and we have a little thin piece of tape on the surface of the channel that diffuses the light. When the light diffuses, if it hits this liquid vapor interface where there's this large change in index of refraction at a relatively shallow angle, it'll just continue going through the test section. It'll keep going to the other side. But for some of the light, some of this diffuse light, if it hits this liquid vapor interface at a large enough angle, something beyond the critical angle, it will totally internally reflect and get reflected back towards the laser. We then have a high-speed camera to pick it up that can operate at pretty high frame rates, and we can get an understanding of how the liquid film is changing inside of the flow. So this is just an example of the type of image you get. So you just get these light rings where we measure the radius between where the laser hit the flow or hit the glass and where you first see this bright region. So where this is first totally internally reflecting. We can then use that radius to get back at liquid film thickness. So again, these are just the types of results that we get. This data was collected by Roman Morse from our lab, looking at just flow across a channel with nothing in it, a pristine channel that was perfectly flat. Here, this shows the base film thickness and the base film thickness in red and the wave thickness in blue, and then an average value. And so as you decrease the quality, we found that the wave height grows, which makes sense, but the base film thickness levels off. And we found that generally it levels off around the thickness of the viscous sublayer if you put it in wall units, which is an interesting finding in this particular experiment. And we're currently evaluating different closure relations to try to understand how does the base film thickness change with fluid properties, looking at some of this water data as well as our refrigerant data. All right, so that gets a little bit at the refrigerant case. It's still a work in progress. We're trying to understand how four-field models can predict refrigerant CHF. We're also extending this in a couple different ways. I'll talk about one of them today. We are looking at flow around an obstruction. This is just a small cylinder in the flow, some imperfection, maybe a fuel pin or something else, or something purposely put in the flow. And trying to understand how the liquid film goes around it. So there's a couple different regions that you can see. We have this obstruction at the bottom. Before the obstruction, the flow is undisturbed. So it looks exactly like it would if there was no obstruction. This is the upstream region. Once it hits the obstruction itself, it forms a wake. And in that wake region, immediately after the obstruction, you get a recirculation zone. You can see these vortexes forming inside of this zone. It's pretty chaotic. And once you get past that general region, you get a very thin liquid film. It's very calm. Generally, as the liquid film gets thinner, the disturbance waves go away. So you get this calm, slow-moving liquid film that eventually dries out inside of this wake region. So you get this small region of dry out downstream of the obstruction. And then on the periphery of the channel, you get this exterior free stream flow that has a lot of these disturbance waves still in it. The film is pretty thick out there. And so when you do have obstructed flow, you tend to get premature dry out, but only in a small region. It's only in this wake region. And so it doesn't necessarily have a huge impact on what's happening at the periphery. In addition to some of these kind of videos, we put in a bunch of thermocouples downstream to try to get an idea of how the heat transfer coefficient varies as you move downstream of the obstruction and what's happening with the fluid itself. So the dry out behavior changes pretty dramatically. This is a similar plot to what we had before. Temperatures on the x-axis, time is on the y-axis, and then there's another y-axis on the x-axis. And there's another y-axis that's the effective heat flux, which is this sort of stair-stepping, kind of increasing the heat flux slowly until we get to a new steady state and trying to see where we hit some sort of critical heat flux. And then there's these different thermocouples. So these are all these different colors or different exterior thermocouples on the surface of the channel. The blue one is closest to the obstruction, and the yellow one is the furthest downstream. And what we find is that you get these temperature spikes. So eventually, at certain locations, you get the flow drying out in this wake region. It starts pretty far downstream from the obstruction. And then as you increase the heat flux, you get this wake region, this dry region extending farther and farther downstream to these closer thermocouples. And every time you do that, you get this increase in the temperature and usually restabilizes. It starts getting pretty hot, but it's not running away in the same way that it ran away in the cases without an obstruction. And just to note, the heat fluxes are lower here, so it tends to dry out sooner. Maybe this has problems around like corrosion and deposition, but you don't get this really dramatic runaway effect. You get kind of a steady increase or a steady decrease in the effective heat transfer coefficient, and it's proportional to the wake size. So if you look at the flow, we did a couple of measurements upstream and downstream of the obstruction. Here's the obstruction. We did these liquid film measurements on kind of equally spaced on both sides for a large and a small obstruction. And these graphs show the ratio of the downstream film thickness to the upstream film thickness. For a large obstruction, the solid data points, and a small obstruction. So generally, we found that the film thickness ratio between kind of this wake region and upstream is not very impacted by the inlet quality. It's not impacted very much by the heat flux. There is an impact on the mass flux coming into this obstruction and the size of the obstruction itself. So if you have a large obstruction and relatively slow moving fluid, the wake region can have, a 20% or so the film thickness of upstream. So there's a really dramatic change in the amount of mass going in the wake region versus the periphery. Whereas the smaller the obstruction, the higher the mass flux, that wake region becomes less important and you don't see dry out as much. So the way that we want to extend our modeling approach to this case, where you have some sort of obstruction or something that's happening in the flow that might deviate or like cause the film to flow in different directions, is we want to split it. So we have this modeling method for section 1, nothing's changed. You're just discretizing in the flow direction and trying to measure how film thickness and these different fields interact with each other. It then hits an obstruction of some sort, and we want to split the solver into different paths. So there's this wake path, which we've generally seen has less mass moving through it. It's moving slower, and it tends to dry out earlier. And then out of that region, in region 3, this kind of free stream, the fluid is behaving differently. There's more mass in that region, and it tends to not dry out as quickly. But to be able to do this sort of thing, we need to answer some questions. So we need to know how the mass is going to distribute around an obstruction. We need to know how the waves are impacted by it. We see generally that the waves split around an obstruction and don't reform in the wake region. They mainly stay out in the region 3. And also, we need to understand mass and momentum transport between region 2 and region 3. So do you get this wake region and they don't interact with each other too much, or do they continue to interact as they move downstream? So those are some questions we're trying to answer now with these obstructions. This is actually a falling film setup, but we took a long exposure video to try to understand how the film is going around some obstruction in a thin liquid film. So what we did is we seeded the fluid with a bunch of particles in it, and then used particle tracking velocimetry to get a velocity profile around it. Here, we didn't use this particular image for it. We tried to kind of track particles, but this shows you You can see these streaks in the flow. You can see the fluid kind of going towards the center, a very slow moving fluid in the immediate wake. This case is not very typical, but shows you kind of a more dramatic kind of velocity gradient around an obstruction. And then we looked at film thickness mapping. So we wanted to understand, if you take a slice of this thing, what is the film thickness across it, so that we can get a better idea of mass flow. As right now, we just had the film thickness. We don't actually know what the mass flow rate is through these different tracks. And so it's hard to actually model it in our four-field approach. So this is the type of data that we're getting out of these experiments. There's a lot of information here. So on the top, you have some obstruction. We're imaging the flow downstream from it. Again, this is a little bit of a weird case. If anybody wants to talk about it, we can. But if you look at different distances downstream from the obstruction and different X positions, we measure the film thickness. So this is this red dashed line in kind of a slice across the flow. And then we also measure the mean velocity gradients across this window to try to get an idea of where is most of the mass. Is it, there's these regions that are both relatively thin. This red line is thin, and the velocity is slow, which makes sense together. And we can get an idea of what is the mass flow distribution downstream from the obstruction. All right, so just a little bit of an outlook for what to do with these types of models. They're potentially powerful. They can help predict CHF, heat transfer coefficients. You can switch between fluids, potentially, if you have good closure relations. But we really need more work on the closure relations portion of it. So for the four-field models, there's not a lot of work around how the disturbance waves interact with different fields of an annular flow. And we need to evaluate performance over a much larger range of fluids and operating conditions to get a really good idea of when is the four-field model useful, and what's its kind of purpose in this larger computational space. And specifically, one thing that our lab is interested in looking at is, how do we take these four-field models and look at other types of questions, either weird boundary conditions? How do you maybe optimize the surface to delay dry out, for example, or what can you do with the surface to change how liquid is distributed between droplets and waves in the base film to try to keep the liquid close to the wall? And then also looking at imperfections, fuel pins, something that's purposely put there perhaps, and trying to understand how fluid goes around some of those things or some of those obstructions without going to very complicated models. So you can still put it in something with interesting boundary conditions, something with a large time trace. They're very fast models, but some of the physics still needs to be resolved. One disadvantage of this approach is correlations are very easy to use. Yeah, it's like a single line of code, maybe it's a couple lines of code, but it's not very difficult to use. This is more difficult, not as difficult as CFD, but not simple. And so one thing that we've done recently is to try to make this modeling framework open source so anybody can use it if they want to, make their own closure relations, try to look at how do surfaces impact things like that. So it's just a screenshot. You can find this open source solver on GitHub. This was developed by some of the students in our lab. Jason Chan was one of the big developers of this open source model, along with Jean-Marie, who's the one who came up with the four-field approach in the first place, Cole Dunbar, Tyler Lee. There's a couple of people working on this that trying to make it easier to use, putting in more closure relations, doing more validation, and that type of stuff. So that's all I have. I'm happy to answer any questions in the last 10 minutes or so. Thank you very much.
Thank you, Allison, for that nice talk. Are there any questions?
I have a question, if I can.
Yeah, please go ahead, Suhas.
Hi, Allison. Nice talk. I'm Suhas from, I'm an assistant professor at Georgia Tech.
Nice to meet you.
Nice to meet you. I probably joined after you graduated.
Yeah.
I was interested in seeing that the base film thickness that you showed was around 5 wall units. Around five wall units. Is that because like the turbulence stresses is highest, like slightly in the buffer region, like so the buffer region is probably like somewhere from 5 to 30 wall units. That's where like you have the highest amount of probably the turbulence stresses. And do you think that is what is responsible for maybe like sort of shearing away the liquid layer in that region, and therefore you see the thickness to be 5 wall units? Was that the expectation?
Yeah, that's our thought. We're not 100% sure what's exactly driving that, but like we know that the waves are turbulent, the base film acts pretty laminar, and we put it in wall units because we thought that probably this buffer region had something to do with where the base film thickness falls, and that's kind of our theory, but we haven't really fully evaluated it or looked at it in a lot of detail. We don't have a great like resolution of what philosophies look like and what other things look like in these experiments. It's kind of we get larger ideas of like the total film thickness, the total base film thickness, and kind of speculate on what's causing it.
I see. Thanks. Yeah.
Other questions?
I had a question. Can I go?
Yes, please.
Okay, yeah. Hi, Allison. Good to see you again. Thanks for the fun talk. You
Yeah.
talked about this idea of a dryout-based critical heat flux being completely separate from film boiling. And my question was, is that specifically for flow boiling only? Or is there also in pool boiling this concept of dryout-based CHFs that are completely distinct from film boiling?
Yeah, I mean, in pool boiling, you typically will go into film boiling. Like to get vapor on the interface, you don't end up with these you could have like, for example, pool boiling of a very thin liquid film, although that's not typically what people do. It's usually like an actual pool. So you don't usually have dry out type CHF in pool boiling situations. You really only go through something like a departure from nuclear boiling and film boiling in that case.
That makes sense. And then just a separate question. When you introduce a single obstacle into your flow boiling system, it kind of reminded me of the pin fins that people are putting in these to enhance flow boiling. So is your idea that just basically, even if it does enhance it overall, it might be introducing like these localized partial dryouts to be kind of aware of? Is that kind of the balance that you're kind of discovering with your research?
Yeah, so there's kind of different situations where you might get these little pins that you care about. In a pin fin type of situation, you could imagine a case where like you're close to dry out, but maybe you can direct the fluid to different regions. Maybe you have these little tiny pockets of dry out, but you don't necessarily care as long as you can re-wet it with another pin close by. So you could try to optimize where you put those pins and direct most of the flow to keep the surface cool, even at very high quality. So there's a big advantage there. There's some drawbacks of like if you don't have a perfectly pure fluid, which is not something most people deal with in an experiment, but is very relevant to more industrial applications, then you can get deposits that form in those dry regions, and then it can cause you a lot of problems downstream. So there's a balance there. You can, even if you have small patches of dry out, if you had a large array of fins, you can really try to keep the surface pretty cool and extend it to a much higher quality. So there's a big benefit of that, and people have shown that in lots of different situations.
Okay, thank you.
Thanks.
Other questions?
Hi, I had a question. Can you hear me?
Yep, I can hear you.
Yes.
So 1 minute. Okay, so hi, my name is Vish. I think Professor Mahvi might remember me from GRC. So I had a question for you. In this particular slides, what you showed, and I joined a bit late, so sorry for that. I did not see anything about the hydrodynamic response. Most of them, what I saw was just looking at the thermal response, which can be the heat transfer coefficient, and the vapor content response, which can be thought in terms of void fraction or the liquid film thickness. But there's a strong synergy between the thermal response, the vapor content, as well as the pressure drop, which is what I want to call it as the hydrodynamic response, because your void fraction measurement goes into the pressure drop relations as well. So what I was just trying to say was that, was there some kind of analysis that you saw to identify how the local pressure gradient changes in this particular region of intermittent dryout, or as you go close towards complete dryout or even partial dryout? Like, did you see any kind of trends in the local pressure gradient when you actually input these vapor content response into that relation?
Yeah, that's a good question. Yeah, so all of these models, they have, like in the momentum equations, for example, there's a pressure gradient in there. And we do measure pressure drop across our test section. Our test section is pretty big, and so we don't get maybe a super resolved pressure gradient at a specific quality because it's evaporating along this channel. We have looked at kind of overall pressure drop and how that changes, but we haven't looked in that data in a lot of detail yet. We just kind of collected it and took some general trends, but need to look at it in more detail. Right now, we don't, like, we use the mixture model to come up with the pressure gradient, so it's pretty simple, and so we haven't quite gotten to that piece yet.
Yeah, but the mixture model is not applicable for separated flows, because mixture model assumes that the slip ratio is 1, but in especially in separated flows, you have higher momentum on the vapor side. So that's why I wanted to tell that in this specific region, this is usually a thing called turbulent vapor laminar liquid region, based on the liquid and the vapor Reynolds number. And the beauty of this region is that the interfacial shear stress is so high because of the additional momentum carried by the vapor, that your frictional pressure gradient even exceeds the theoretical maxima, which is basically your frictional pressure gradient should go from single phase liquid to single phase vapor, but here it even exceeds the single phase vapor itself, and then it comes down. So there is a little bit of physics that can actually help with this investigation, if you can, like, if you and your team decide to go in that direction.
Yeah, thanks for the suggestion. We'll look at that in a little more detail.
Other questions? Okay, well, if not, thank Allison again for her talk.
Thank you very much.